Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of cloud computing. We'll dive into key concepts like rational operations, enterprise batch processing, example applications of MapReduce. Let's get started. Slide 1. Relational operations in cloud computing. Cloud computing has revolutionized how we store and process relational data. But what exactly are relational operations in the cloud? Relational operations refer to structured queries performed on cloud databases that follow the Relational Database Model (RDBMS). These operations ensure efficient data retrieval, filtering, sorting, and aggregation in cloud environments where data is distributed across multiple servers. Let's go over some of the most important relational operations used in cloud computing. 1. Selection, sigma. This operation retrieves specific rows that match a given condition. Example, if we want to fetch all customers aged above 30, we use selection. 2. Projection, pi. Instead of retrieving all columns, projection helps in selecting only necessary attributes. Example, instead of fetching an entire employee record, we can retrieve only names and salaries. 3. Join. This is crucial in relational databases, as it combines data from two or more tables based on a common field. Example, a customer table and an order table can be joined to find out which customer placed which order. 4. Aggregation, sum, avg, count, max, min. These operations help in summarizing data, like computing total sales or finding the average salary. Example, some operation can be used to calculate the total sales revenue for a company in a given year. 5. Sorting, order by. This arranges data in a meaningful order, either ascending or descending. Example, sorting a list of products by price from lowest to highest. 6. Grouping, group by. Groups data based on a common attribute. Example, categorizing employees by department to find the total number of employees in each department. 7. Set operations, union, intersect, difference. These are used to combine or filter multiple datasets. Example, union operation can be used to merge two customer databases into one. Relational operations play a critical role in cloud computing, where services like Google Cloud Spanner, Amazon Aurora, and Azure SQL Database provide scalable relational database solutions. Slide 2. Challenges in relational operations on cloud. Despite the benefits of relational operations in the cloud, they come with unique challenges due to the distributed nature of cloud computing. Let's look at some key issues. 1. Scalability issues. Traditional relational databases were designed for single-node execution, but in cloud computing, data is stored across multiple servers. Scaling relational operations while maintaining performance is a big challenge. 2. Consistency versus availability trade-off. In a distributed environment, there's a balance between maintaining strong consistency and ensuring high availability. According to the CAP theorem, achieving both simultaneously is difficult. 3. Latency. Query execution in the cloud often involves fetching data from multiple nodes, leading to delays. Large-scale joins and aggregations can increase query response times. 4. Security concerns. Storing relational data on the cloud raises security risks such as unauthorized access and data breaches. Encryption and access control policies help mitigate these risks. 5. Data redundancy. Cloud databases often replicate data for fault tolerance, but excessive redundancy can lead to storage inefficiencies and synchronization issues. 6. Complex query optimization. Query optimizers must efficiently execute relational operations across distributed nodes, which requires advanced indexing and partitioning techniques. 7. Integration with big data. Many cloud applications combine structured relational data with unstructured NoSQL data. Ensuring smooth interaction between RDBMS and NoSQL databases is a significant challenge. To address these challenges, cloud providers implement solutions like distributed indexing, caching, sharding, and replication strategies to optimize relational operations in cloud environments. Slide 3. Enterprise batch processing in cloud computing. In enterprise applications, companies handle vast amounts of data that cannot be processed in real time. This is where enterprise batch processing (EBP) plays a crucial role. Batch processing involves executing large-scale data jobs in scheduled intervals, typically overnight or during low traffic hours, to optimize performance. Unlike real-time processing, batch jobs process data in bulk, ensuring efficient resource utilization. Key features of enterprise batch processing. 1. Automated execution. Jobs run on predefined schedules, eliminating manual intervention. 2. Scalability. Cloud-based batch processing can scale to handle terabytes or even petabytes of data efficiently. 3. Fault tolerance. If a node fails, the job resumes from the last checkpoint, preventing data loss. 4. Parallel processing. Tasks are broken down into smaller units and executed across multiple servers simultaneously. 5. Time efficient. Since batch jobs run outside peak hours, they reduce computational load during business operations. 6. Integration with data warehouses. Cloud platforms like Amazon Redshift and Google BigQuery support batch processing to analyze large datasets. 7. Cost-effective. Many cloud providers offer serverless computing, allowing organizations to pay only for the computing time used. Example. One of the most common examples of enterprise batch processing is payroll processing. At the end of each month, organizations compute and distribute salaries for thousands of employees using batch jobs instead of processing each salary transaction in real time. Slide 4. Batch processing versus real-time processing. 1. Execution mode batch processing. Data is collected, stored, and processed at scheduled intervals or in large chunks. Jobs run periodically, e.g., daily, weekly, or monthly. Example. A payroll system that calculates salaries at the end of each month. Real-time processing. Data is processed immediately as it arrives, with continuous execution. Suitable for applications requiring instant insights and quick decision-making. Example. A stock trading platform updating prices in milliseconds. 2. Latency. Batch processing has high latency, meaning results can take minutes, hours, or even days. Best for scenarios where immediacy is not a priority. Example. Generating monthly bank statements. Customers don't need them every second. Real-time processing offers low latency, producing results within milliseconds or seconds. Required when immediate actions are necessary. Example. A fraud detection system identifying suspicious credit card transactions in real time. 3. Scalability. Both batch and real-time processing are highly scalable, but they scale differently. Batch processing scales well by distributing jobs across multiple servers. Real-time processing uses distributed streaming architectures to process data continuously. Example. Cloud platforms like Apache Hadoop scale batch jobs, while Apache Kafka scales real-time event streaming. 4. Use cases. Batch processing. Best for tasks that don't require immediate action. Examples include payroll processing, billing systems, and periodic reporting. Example. E-commerce sites generating sales reports at the end of the day. Real-time processing. Used when immediate data-driven decisions are required. Common in fraud detection, live analytics, and monitoring systems. Example. Self-driving cars processing sensor data in real time to make driving decisions. 5. Resource usage batch processing. Uses high but predictable resources since jobs run periodically. Can be optimized for cost efficiency, e.g., running during off-peak hours. Real-time processing uses high and dynamic resources because data flows continuously. Needs powerful computing infrastructure to keep up with real-time demands. 6. Example batch processing example. A bank transaction summary is generated at the end of the day, showing all transactions in a consolidated report. Real-time processing example. Stock market price updates occur instantly as trades happen, ensuring traders see the most up-to-date prices. Key takeaway: batch processing is suitable for periodic, large-scale computations, whereas real-time processing is essential for instant data analysis and immediate actions. Many modern cloud applications use a hybrid approach, leveraging both batch and real-time processing for maximum efficiency. Slide 5. How MapReduce works in cloud computing. Now, let's discuss MapReduce, a powerful framework for processing large-scale data in cloud computing. It follows a divide-and-conquer approach, breaking down complex computations into parallel tasks executed across multiple nodes. How MapReduce works. MapReduce consists of two main phases. 1. Map phase. The input dataset is split into smaller chunks and processed in parallel. It transforms data into key value pairs. Example: if we want to count the number of times each word appears in a document, the map function will emit pairs like cloud, 1, computing, 1. 2. Reduce phase. The reduce function aggregates key value pairs to generate final results. Example: the final output might be cloud, 3, computing, 5, meaning cloud appeared 3 times and computing appeared 5 times. Example: Google uses MapReduce to process billions of web pages and update its search index efficiently. Slide 6. Advantages of MapReduce in cloud computing. MapReduce has gained popularity in cloud computing due to its ability to process vast amounts of data efficiently. Let's explore its key advantages. 1. Scalability. One of the biggest strengths of MapReduce is its ability to scale horizontally. It can distribute processing across thousands of machines, making it ideal for big data applications. Example: Google search index updates are processed across thousands of servers using MapReduce. 2. Fault tolerance. Cloud environments are prone to hardware failures, but MapReduce automatically detects and recovers from node failures. If a server crashes, its tasks are reassigned to another node. 3. Parallel processing. The framework splits large datasets and processes them in parallel across multiple nodes. This significantly reduces processing time compared to traditional sequential processing. 4. Cost-effective. MapReduce runs on commodity hardware instead of expensive high-performance servers. This makes it a budget-friendly solution for processing large-scale data. 5. Flexibility. Unlike traditional databases that mostly handle structured data, MapReduce supports structured, semi-structured, and unstructured data. Example: it can process logs, text files, images, and even video metadata. 6. Security. Cloud-based implementations of MapReduce often include authentication, encryption, and access controls to protect sensitive data. 7. Optimized for cloud. Cloud platforms such as Google Cloud Dataflow, Amazon EMR, Elastic MapReduce, and Apache Hadoop offer seamless integration with MapReduce for large-scale data processing. These advantages make MapReduce a powerful tool for handling massive datasets in the cloud. Slide 7. Disadvantages of MapReduce. Despite its benefits, MapReduce is not perfect. It comes with several challenges, particularly in cloud environments. Let's look at some key disadvantages. 1. High latency. MapReduce follows a batch processing approach, meaning results are generated after the entire job is completed. This makes it unsuitable for real-time analytics where instant insights are required. 2. Complex debugging. In distributed systems, tracking errors across multiple nodes is difficult and time-consuming. Debugging requires specialized tools and expertise. 3. High disk I/O. Since MapReduce frequently reads and writes intermediate data to disk, it suffers from slow performance compared to in-memory processing frameworks like Apache Spark. 4. Requires advanced skills. Working with MapReduce requires knowledge of Hadoop, Java, or Python, making it less accessible for beginners. 5. Memory intensive. Processing large datasets requires optimized memory allocation to prevent excessive swapping and performance degradation. 6. Not ideal for small data. The overhead of setting up a MapReduce job is too high for small-scale tasks, making it inefficient for quick computations. 7. Batch-oriented. Unlike Apache Flink or Spark Streaming, which can process continuous data streams, MapReduce is limited to batch jobs only. Due to these limitations, many organizations are moving towards more advanced frameworks like Apache Spark for data processing. Slide 8. Applications of MapReduce in cloud computing. MapReduce is widely used across industries for processing large-scale data. Let's look at some real-world applications. 1. Search engines. Google uses MapReduce to crawl and index billions of web pages, ensuring search results are always up to date. 2. E-commerce. Amazon and other online retailers analyze customer purchase history to recommend products based on past behavior. 3. Social media. Platforms like Facebook and Twitter process trending hashtags, user activity, and ad targeting data. 4. Healthcare. MapReduce is used in genome sequencing and medical research to analyze DNA data. Example: bioinformatics platforms use it to process massive genetic datasets. 5. Financial services. Banks use MapReduce for fraud detection, risk analysis, and transaction monitoring. 6. Cybersecurity. It helps in detecting anomalies in network logs, identifying security threats in large-scale IT infrastructures. 7. IoT data processing. With billions of IoT devices generating continuous data, MapReduce is used for log analysis and predictive maintenance. These applications highlight how MapReduce is shaping the future of data-driven decision-making across industries. Slide 9. Comparison of Hadoop MapReduce versus Apache Spark. As big data processing evolves, Apache Spark has emerged as a strong alternative to Hadoop MapReduce. Let's compare the two frameworks. Processing type. MapReduce is purely batch-based, while Spark supports both batch and real-time streaming, making it more versatile. Speed. Spark is much faster because it uses in-memory computation, reducing disk I/O. Example: Spark can process gigabytes of data in seconds, whereas MapReduce may take minutes. Ease of use. Spark provides a simpler API with Python, PySpark, and SQL support, whereas MapReduce requires complex Java-based code. Use case. MapReduce is still used for traditional big data tasks like log processing. Spark is preferred for advanced analytics, machine learning, and streaming applications. Due to these advantages, Spark is gradually replacing MapReduce for many data-intensive tasks. Slide 10. Future trends in cloud-based data processing. Cloud data processing is rapidly evolving. Let's explore some exciting future trends. 1. Serverless batch processing. Cloud providers are shifting towards serverless computing, where batch jobs run dynamically without provisioning dedicated infrastructure. Example: AWS Lambda automates data processing with minimal operational costs. 2. AI-powered optimization. Machine learning algorithms are being used to improve query execution and data indexing in cloud databases. 3. Edge computing. Instead of processing data in centralized cloud servers, edge computing allows batch jobs to run closer to IoT devices, reducing latency. 4. Hybrid processing models. Many companies are adopting a mix of batch and real-time processing to get the best of both worlds. Example: fraud detection in banking uses real-time monitoring with batch-based risk analysis. 5. Quantum computing. Though still in its early stages, quantum computing has the potential to revolutionize parallel data processing. 6. Energy-efficient data centers. Cloud providers are focusing on sustainable energy and optimizing cloud infrastructure to reduce power consumption. 7. Zero Trust security. Stronger security models are being developed to ensure data privacy and protection in distributed environments. These trends will define the next era of cloud-based big data processing.